So gel electrophoresis is a technique through which we can run a DNA molecule or a protein molecule, and these molecules will be separated according to its size. Okay. To separate different DNA molecules or protein molecules vis-a-vis their size, we use this gel electrophoresis technique. Basically, in our lab, we will be dealing with two electrophoresis techniques. One is the Agarose Gel electrophoresis. And the second one will be SDS polyacrylamide gel electrophoresis. These are the two techniques that will be dealing here, and these techniques are the backbone of a molecular biology laboratory or you can say a biotechnology laboratory, because when we do a PCR, when we extract genomic DNA from a fungal plant cell or a bacterial cell, when we isolate a plasmid DNA, when we run a real-time PCR, for everything we need this Agarose Gel electrophoresis to confirm our results. Okay, so this is the basic backbone technique that we'll be studying today, the Agarose Gel electrophoresis. So before you start an experiment, you have to have the prerequisites or the materials that you will require for this experiment. Okay. And before moving to the materials, you need to understand the principle of this technique. Say for example, this is a Agarose gel that is made of agarose. That's why it is called as Agarose Gel electrophoresis. Okay, this agarose is a purified form of agar-agar, and that's obtained from Gelidium or Gracilaria, you know that, right? So agarose is a more pure form of agar-agar. So we use this agarose as a gel matrix. So this gel, this agarose gel, we run in an electrophoretic tank, okay, that has a negative electrode and a positive electrode. Okay, and what we're going to run here, we're going to run our DNA here. So if you see the structure of a DNA, it's a double helix, okay, and the backbone of this DNA is made up of sugar and phosphate, right? Now phosphate has a net negative charge, okay, and you have one phosphate molecule associated with each base and two phosphate molecules with a base pair. Okay, when we read DNA, we say base pairs, like 100 base pairs, 200 base pairs, because the DNA is double stranded and each base is paired. If you have an A here, you have a T here. If you have a G here, you have a C here. Okay, and these two strands are connected with the help of a hydrogen bond. So there are many bonds that are involved in DNA. Okay, you have the hydrogen bond that connects the two strands of DNA. Then you have a phosphodiester bond that connects this backbone. Okay, then you have a glycosidic bond that connects a sugar moiety with your. If you see the structure, you have a deoxyribose sugar, okay, and then you have a base. This is nitrogen's base. So this is your glycosidic bond, okay. Then you have a OH here because this is DNA, okay, and you have CH2, O, and you have P here. So the negative charge is because of this phosphate. So DNA has a uniform negative charge, okay, due to this phosphate backbone. That's why when we put this DNA in wells in an agarose gel, okay, and apply the electric field, say 100 volts, So DNA being negative in charge will be repelled by this negative electrode and will be attracted by this positive electrode. So the DNA will run in the gel like this. The molecules that are bigger, will be dragged back. So these bigger molecules will not be able to travel much, but the smaller molecules will be able to move through this matrix. Okay, agarose gel makes a matrix kind of a thing. Okay, so this matrix, through this matrix, bigger molecules will be able to move slowly, while as the smaller molecules will be able to move faster in this gel. Okay, so and we'll be able to resolve the gel according to its molecular weight. So more the molecular weight, the lesser the mobility. Less the molecular weight of a DNA fragment, more the mobility. ठीक है? So how we do this experiment? So this is the principle behind this. So you have the prerequisites of an agarose gel. What you require. First and foremost thing in chemicals, what you require in agarose gel is your TAE. Okay. Here T stands for tris, A stands for acetic acid, and E stands for EDTA. This is the buffer that we run our gel in, and this is the buffer in which we make our agarose gel. For example, the concentration of this agarose is 50x. Oh, sorry, this TAE is 50x, because this is usually required in large quantities in a biotechnology lab, and we have to keep a stock of this. Okay, this 50x we call as stock solution, and what we'll be using in our experiment will be 1x concentration. Okay, so you'll simply dilute it in water, and you will make 1x concentration. So now we have to make an agarose gel. So what we do, we take a flask and we measure agarose. It comes in the form of a powder. Okay, so if we have to make 1% of agarose gel, that means we have to add 1 gram in 100 ml is 1%. If we want to make, okay, the concentration of the gel is determined by what DNA we are running in the gel. If the DNA is of high molecular weight, we'll use a low concentration gel like 0.7%. If we have to run smaller molecules, we will make a higher concentrated gel, say 2%. So it depends on the type of molecule you want to run, what is your experiment, so that will determine what will be the concentration of your gel, agarose in the gel. So for example, we are making 1% gel, so you'll get 1 gram in 100 ml of TAE. And then we will add, this TAE is how much we'll use, 1x. Okay, if you are making, so you'll add agarose 1 gram, and then you'll pour in 100 ml TAE. You can use TBE also, tris, boric acid and EDTA. Okay, but boric acid is a little bit costlier, so in our lab we use acetic acid. So you know that your stock solution is 50x, and you have to make a 1x solution of 100 ml. How will you do it? So what you do, you keep this formula, you remember this formula by heart, and this formula you can use anywhere in your day-to-day experiments. The formula is working concentration by stock concentration into the final volume. So working concentration is the concentration that we require at the end. That's the end product. So this is your gel. That here in this case it will be 1x. And the stock from which we took it is 50x. And the final volume we want to make is 100 ml. So x will go, 0 will go. That means 2 ml of this 50x you will require, okay, to make 1x gel, 1x TAE. And in this 2 ml you will add 98 ml of water, distilled water. So total will be 100 ml, and now the concentration will be 1x. Okay, so 1 gram of agarose and 1x TAE. You add and you heat it, you boil it. You boil it for 2 minutes to 3 minutes until you see that agarose is dissolved, and then you let it cool. Okay, you cool it so you'll be able to touch it with your bare hands, like say about 50 degrees centigrade. You don't have to overcool it, because if you overcool it, the gel will solidify. We do not want the gel to be solidified in this flask. We want to solidify it in a cast, okay, gel cast, what we call it. So the reason why we use TAE is because you have this tris here. Tris is a buffer, okay, and its pH is 8. It's a buffer, its pH is 8. It's used as a buffer, okay, to maintain the buffer conditions of the system. System क्या है? You have this electrophoretic tank जिसमें आपका TAE buffer है, then you have a gel, agarose gel. So tris will maintain the buffer condition, okay, and the quality of the buffer is that it undoes any change. If there happens a change, it undoes its change and brings the pH back to 8. Okay. The principle of using the acetic acid is that it provides conductivity. Okay, the gel has to run, they ought to be connected. Okay, if you have two electric wires and you have a bulb, and unless and until you press the switch, you connect them, the bulb will not light up, right? In the similar case, if there is no conductance between these electrodes, the gel will not run. So acetic acid provides this conductivity in the solution, so the gel runs. There is a passage of current through the system. And third is EDTA. Okay, EDTA is a chelating agent, and if somehow while running our gel there are some DNases that creep in, okay, some bacteria falls in the our system, okay, they produce DNases, okay, our hands have DNases and RNases, they always produce that. So to protect our gels, to protect our DNA from degradation, we use EDTA. Okay, EDTA chelates the metal ions, and metal ions are important entity of a holoenzyme. So you have an enzyme or a holoenzyme. In this case, the holoenzyme is your DNase. Okay, it's made up of apoenzyme plus a cofactor or a coenzyme. So if you take this cofactor out, this apoenzyme, it will render it non-functional, and this will not have any activity. So prevent the activity of DNases in our system, we use EDTA. It chelates our metal ions, in this case magnesium, and it renders our DNA as inactive, so that now our DNA is safe, it will not be degraded in the system while it's running, right? So you have the gel, you have the TAE, you heat it up. Once you heat it up and bring it down to 52 degrees centigrade or 50 degrees centigrade, then you put up a cast. Cast is nothing but have you made like cakes? You bake cakes, or you make what do you call ice cubes at home? So you have that cast, right, in which you put water, and when it freezes, your ice cubes are in the shape of your that cast. Similarly, a gel cast is nothing, okay, but a hollow rectangular cast, in which we, if we make it in 3D structure, it will be like this. Okay, this is the top view, this is the top view, and then you put, once you put pour the melted agarose gel in this, then you put a comb. You put a comb in the gel, okay? So the comb is not the comb that we use to comb our hair, but it's a comb. When we join labs, you'll be doing these experiments. So this is a comb shaped, okay, plastic material that we put in the gel, and then let the gel solidify. When the gel solidifies, we take this comb out, and then you have hollow wells there. We load our DNA into those wells, okay. So you put your gel here, let it solidify. When the gel solidifies, we take it and put it in the tank. And these are your wells that are visible here. All right. So then what we do, we load our DNA into these wells. Okay, before that. So once this agarose melts at, we bring it down to 52 degrees centigrade or 50 degrees centigrade, we add ethidium bromide in this. Ethidium bromide is a carcinogen, it's a neurotoxic, but it has a property of enhancing the fluorescence of, the DNA has the property of enhancing the fluorescence of ethidium bromide. This helps us visualize the DNA in a gel. How? When we add this in the gel, and when DNA runs, so for example, if say this is your phosphate sugar backbone, this is another phosphate sugar backbone, okay. The bases, the nitrogen bases are perpendicular to this phosphate backbone, okay. You'll be able to see it like this if I draw DNA. This is a sugar phosphate backbone. You have, these are nitrogenous bases. These are perpendicular to your sugar phosphate backbone. This is the sugar phosphate backbone, and these are your nitrogenous bases. So they are like they're stacked on each other like this with an angle of 12 degrees, say. We call this, due to this change in angle, okay, the DNA becomes a ladder shape and not a staircase shape, not a ladder shape, okay. So once these bases are like this, the structure of your ethidium bromide is also planar. So what happens between two bases, it intercalates. We call this process as intercalation. Intercalation of the is a process through which the ethidium bromide gets incorporated between the bases. So this ethyl bromide being planar in structure and the bases being planar in structure, it can easily squeeze through the bases and is there. Once, and this has a property that it fluoresces under UV. So once the gel is run, this ethyl bromide is intercalated in the DNA, and when we put it on a UV transilluminator for visualization, we will see that the bands fluoresce. The bands fluoresce because of the ethyl bromide. There's a term we call as fluorescence enhancement. Okay, some molecules have a property of enhancing the fluorescence of other molecules. Like in this case, DNA is a fluorescence enhancer of ethidium bromide. Okay, some molecules are fluorescence quenchers. They quench the fluorescence of others. Okay, they stop other molecules from fluorescing. Okay, in this case, DNA acts as a fluorescence enhancer. Okay, so that's why we are able to see these bright DNA bands at the end. So we add this ethyl bromide. Okay, the working concentration of this is 0.5 microgram per mil. Okay, and the stock solution of ethyl bromide is 10 milligrams per mil. Now if I tell you to calculate at your places that the stock solution of ethyl bromide is 10 milligram per mil and working is 0.5 microgram per mil, how much of this you will add in a 100 ml solution of Agarose Gel TAE? Can you calculate it? And tell me the answer. So the working is 0.5 micrograms per mil and the stock is 10 milligram per mil, and this we are adding in 100 ml of our boiled Agarose Gel TAE mixture. And you have to ensure that once we do not add ethyl bromide before boiling, we add it after it has cooled to 52 because it's heat labile and heat can degrade it. That's why we would add it afterwards. You should ensure this. Okay, so if you calculate this, how much it will be equal to? Gg ml 10 10. So you have 5 this micro and this liter, right? So 5 microliter of 10 milligram per mil you will add in your 100 ml gel, so that the final concentration is 0.5 micrograms per mil. Okay, not more, not less. So you added this and put the DNA in the cast, and then after say 10-20 minutes the gel will solidify and you will put the cast in the electrophoretic tank. This is called as electrophoretic tank. Now your gel is there. Okay, now you have to load your samples, DNA samples. So this gel, when you put it in the tank, if we see the side view, this is a small, this is your gel. I'll make it in other color. This is the side view. Okay, okay, this is your well. Only one will be visible because we are looking from this angle. And we add buffer 1x TAE up to, we submerge the gel. Okay, we put the buffer okay, over the gel. What we call it, we submerge it in the buffer, right? So now when you're adding DNA with a pipette, this DNA will float back. If you put it in the well, it will come out. Okay, because it's not heavier enough. The density of the DNA and the buffer is the same, so it will come out. So what we do before loading the DNA in the gel, we add bromophenol blue, or what we call as a loading dye. Have you read the story Monte Cristo?
No, sir.
Okay. Monte Cristo? Yeah, okay. There was this guy,
No, sir.
okay, who was falsely implicated in something, and then he was sent to Chatudiaf, was an island, it was kind of a prison. And then how he escaped, so his roomie died. Okay, there were two men in the cell, he died. So what he did, he took the body of that roomie out and put himself in the coffin. Okay, so what usually they do, they make these graves, ocean graves, okay, or water graves. They tie a stone to its legs, okay, a huge stone, so that when they throw the body, it will not float up, it will submerge, and the fish and it will eat it, and it will decay and get degraded. Okay, so what he did, he put himself in the coffin of that dead man, and then they threw him, thinking that he's the dead man. So they tied this to his legs, tied a rock or a big ball of that iron to his legs, and threw him in the sea. Okay, so luckily he had that pocket knife, how he was able to chew himself out, whatever. So why I'm telling you this, the same thing is here. So what we do, we add this loading dye with our DNA before loading into the well, because this loading dye makes the DNA heavier. Once it's heavier, it will settle in the well, right? So why this is, there are in fact two constituents of the loading dye. One is your bromophenol blue, and then you have sucrose or glycerol, 30%. This sucrose or glycerol is the thing that makes the DNA heavier, because its density is higher than water. And bromophenol blue is what we call as a tracking dye. This helps us track how much the gel has run, because once we start running the gel, so how will you know that the DNA have not overflowed, okay, have not surpassed the mark and have flown into the tank? So what we do, we add this bromophenol blue or xylene cyanol. They are both trackers. They give a blue impression. It's also negatively charged, so and it's smaller, it moves ahead of the DNA. So once this blue line reaches here towards the end, we know that our gel has run enough. Now we can stop and visualize our DNA. Okay, so there are two reasons why we add loading dye with the DNA. Number one, it makes it heavier because of the presence of 30% sucrose or glycerol. Okay, and bromophenol blue or xylene cyanol, they are called as tracking dyes. They help us to track the DNA. Okay. The concentration of bromophenol blue is 0.25%, or xylene cyanol is 0.25% in the loading dye. So now what we did, we took our DNA sample on a parafilm, put it here, okay, again, this loading dye is 6x, and we have to use 1x, okay? So you'll add accordingly. So if you have kind of 25 microliters of this, so you do the math, how much microliter of this loading dye will, 1 by 6 into, say final is 30, so 5 microliters of loading dye you'll use with 25 microliters of DNA, that will be sufficient. You mix them on a parafilm, and then you take it out with the help of a pipette and slowly pipette it into the valve. So initially, if you are doing it for the first time, you'll be able to dislodge the valve, you'll be able to put the pipette too deep and you'll puncture the valve. So initially it will happen, but slowly with time you'll become masters of this, and it's very easy, it's not that difficult. So once you have loaded all your samples in the DNA, you will load a molecular weight ladder also. So molecular weight ladder you use because, for example, I have to see that what is the length of my phone. So what do? I put a scale besides it, right? The scale will tell me, okay, how long it is, right? Similarly, we put a molecular weight ladder in which we know what are the different fragments and what is the size of those fragments. So when you run the gel completely, so here we say it's molecular weight or molecular marker, we also call it as marker or ladder. Once the gel runs and your loading die or drying die reaches the end, we take the gel out and we put it on a transilluminator. UV transilluminator is nothing but it just gives us UV light, and under UV light your DNA will fluoresce because of the presence of ethidium bromide in the DNA that we have initially added at the time of making the gel, right? So it's easy. Making a gel and running a gel is just like making a cup of tea. Simply while making a cup of tea, you add sugar, water and milk, okay, and boil it. Similarly, in making Agarose gel, you make Agarose, TAE, ethidium bromide, and you boil it and put it in a cast. Right? It's simple. It's not that difficult. So that's why if you're a good scientist, you are a good cook also. So now, when you have run the gel and you have taken out the gel, it will be just like this, okay? Though it will be kind of watery in color, and you put this gel on a transilluminator or a gel dock. We have a gel dock, or also called a gel documentation system, okay? It has a built-in camera, everything. You can image the gel after running it. So now you have a gel and you have, these are the valves. So in this you loaded the molecular weight marker, right? Or the DNA ladder, we also call it. So these are commercially available ladders, and you know that when they supply you with the ladder, they will tell you that the lower band is 100 base pairs. Then you have 200 base pairs, 300 base pairs, 500 base pairs, then 1 kb, 3 kb, 5 kb, 8 kb, 9 and 10. Okay, so the higher you go, more molecular weight. Like here 10 kb here. 1 kb is 1 kilobyte, 1000 base pairs. Okay, so this is 10 and more 3 10,000 base pairs. Okay, here you have 100 base pairs. So 100 base pairs. So it's commercially available. You have a mixture of all these DNA fragments, and then they mix it. And when you run it on the gel, it will resolve according to its molecular weight, and you have 100. The smallest molecular weight will be at the bottom because it will move faster than the larger molecule, that is 10 kb, because that's larger. Now a question arises that this 10 kb has more charge, right? Because it has 10,000 made of 10,000 base pairs and 20,000 phosphate molecules. Okay, one base has one phosphate, one base pair has two phosphate. So you have here 20,000 or 20K, 20,000 phosphate molecules, while in this case you have just 100, let's say 200, 100 to 200 phosphate molecules. So this is a higher charge in comparison to this. So why doesn't this 10,000 move faster than the smaller one? Can anyone tell me the answer? Anyone? No? None? Because even though the number of phosphate molecules are more, but charge to mass ratio is the same in both the cases. How? So if this is 10,000 base pairs, it has 20K phosphates. So 10,000 by 20,000. So the charge to mass ratio is 1 by 2, right? And in this case, you have 100 by 200. And again 1 by 2. So the charge to mass ratio in both, that means they'll be pulled with the same force, same amount of force. Force will be equal, but since the larger molecule will be bulkier, so it will be difficult for this larger molecule to move in between the matrix of the agarose gel. While the smaller molecule, it will be able to slowly traverse between the matrix of the gel. So that's why that moves faster, and the larger molecules is dragged behind and moves slower, right? So now we have put it on the gel, and then if you are running a genomic DNA that you have isolated from an organism, genomic DNA is the whole DNA that you isolate from an organism, say a fungus, a plant cell, bacteria, okay, yeast, human cell. When you run the DNA on a gel, you will get a band that will be near the well, because genomic DNA is a high molecular weight DNA that will always be moving near the gel. Okay, it will be towards the wells. And if you have a smaller molecular DNA virus, you isolate a DNA from it, like so, that it will be smaller in size, so it will move further, right? So some of the precautions you have to take while you do this experiment is, I send you a list of do's and don'ts in laboratory, that you should have an apron, okay? You should not keep your hair dangling in case of girls, because you have Bunsen burners there, they may catch fire, it's a hazard, okay? You should wear gloves if you are dealing with ethyl bromide or any toxic chemicals. If you are using chemicals that have fumes like methanol, they are toxic to eyes, you can use a face shield or a goggle to prevent your eyes. So there is do's and don'ts list that I have sent you. You can go through it. Okay, your shoes should be, your feet should be covered with shoes. Chappals are not allowed, or slippers are not allowed in the lab. Okay, and you have to take utmost care with ethyl bromide because it's carcinogenic. It causes frame shift mutations, and if you overuse it over time without precautions, it will be hazardous to your health.